Now watch what you are about to see incredibly carefully. As you can see, a ball bearing goes up, just goes out of shot, and then it falls back down, and incredibly it lands back on top of the tube. The tube, by the way, is a Steve Spangler geyser tube. Geyser. What you just saw was actually antacid powder being dropped into Diet Coke. But the principle's the same. It actually works better for Mentos though. But still, it was pretty cool that the ball bearing managed to land back on top of the tube. Now anyway, using the tape measure that you can see in this shot, and also the frame rate, which was 120 frames per second, I can plot a graph of displacement against time. So in this case, displacement is a measure of how high the ball bearing is above the tube in meters. And here is the graph. So using Excel's curve fitting contraption, I can find an equation relating displacement to time. Now if I differentiate the graph of displacement against time, I get a graph of velocity against time, and this video is getting incredibly sad, but we'll roll with that. Now if I differentiate the velocity time graph, I get a graph of acceleration against time, and by Newton's second law, F force equals mass times acceleration. So if I multiply the equation by 0.014 kilograms, which is the mass of the ball bearing, I can make this graph which shows how the resultant force of the ball changes with time. The resultant force, F_rus, is T, the thrust, minus mg, which is the weight. So the thrust produced by the Coke is actually equal to the resultant force on the ball bearing plus the weight of the ball bearing. I have my thrust against time graph here, so the area under that is actually the change in momentum that the Coke and antacid powder reaction has produced. I find this area by integrating with respect to time, and that gives me about 0.25 numbers, etc. kilograms meters per second. I want to find the maximum mass that this reaction could send into space, which is a natural thing to be doing with your Saturday afternoon. This reaction would be able to send a 2.5 times 10 to the minus 5 kilogram mass to a point in space. Using wolframalpha.com, I found out that the reaction could send 8 snowflakes into space. So if NASA are ever in need of a fuel that is about as heavy as current fuels, but even so, it can't produce enough thrust to carry its own weight and can only just about launch 8 snowflakes and nothing else under ideal conditions into space. Well, they should talk to me. Here's another test I did using coral sand instead of antacid powder. Now this time the ball doesn't land back on top of the tube because the reaction is a lot more powerful. So I only have data for the first part of its motion, but I can use the same graphing process as before, and this shows me that the maximum thrust, at least in the initial period of its motion, is almost 0.85 newtons, which is about enough force to lift up an apple. I like apples. You know, I might do a video about apples actually. So stay tuned to Tom T Physics if this sort of thing, yeah, if you like this sort of thing.